So let's say that as you're working through your career, you end up having to take a sales position somewhere, and part of that job is traveling around the country, having to hit a few locations, like, say, Dallas, Atlanta, Chicago, and LA from a home office in Seattle. And you and your company want to be able to figure out how you can hit those locations in the most efficient way possible. Because you have to reach all five of them for whatever it is you're selling, whatever it is that you're working with. And you want to be able to do that in the most cheap way that you can. At the very least, you want to be able to save some money there. You might also want to save some time, but we're going to focus on the finances here because you are in sales. Where what we need to do then is find a Hamilton cycle, a Hamilton circuit, through those 5 locations that minimizes the cost, where this is essentially the idea of what's called the traveling salesperson problem, where what we want to do is be able to find an optimal Hamilton cycle through a weighted graph. Where one thing I do want to mention specifically is that because of all the things it sets up with these complete graphs, it presents the traveling salesperson problem as being specifically in the context of a complete weighted graph, which it's a nice one to work in because finding these things, as I said earlier, is incredibly difficult in general. But just understand that while the book was reasonable in being inaccurately specific, it is inaccurately specific. And you can, and a lot of people do, put a lot of time and research into being able to describe solutions to the traveling salesperson problem in more general cases. Something I've worked on in particular, and I know that others have as well. But anyway, here we're going to finish this week talking about a couple of methods for how we can work our way towards potential solutions, or at the very least approximations, in the context of the complete case.